Well, as we understand that there's a lot of data available in today's context, and any activity as a human being that we do generates a lot of data. So think about a mobile phone. If you actually do a call, the amount of data that it generates, it finds it actually we get to know from who's calling whom, what is the length of that call. If you are sharing some data, we know what was the length of the data packet. So there's a huge history for each and every transaction that we do. Similarly, if you think about an ATM, so if you moment you put in your card into your ATM and withdraw cash out of it, there's a huge amount of data trail which actually gets generated. So data is getting generated, number one. Number two is that data can be captured very easily because now the storage costs have decreased substantially, and it is very easy to actually store lots and lots of data very easily at any point in time. So capturing data. So first and foremost, generation of data is very easy. Next, you have got a lot of sensors available in today's context which can actually capture this data. Third is that we can store this data very easily. So these three things are very easy in today's context. So the input part of the data is very easy. So I can get the data, I can store the data, I can capture the data, I can store the data. Now the question arises that what do I do with this data after this? I should be able to analyze the data just as we saw. So either we should be able to describe a particular event, or we should be able to forecast a particular event, we should be able to predict a particular event, or should we be able to optimize a particular event. So that is the basic understanding. Now, if we talk about uh, if we are talking about things by the way, this slide, some of them I've been taking from the MIT's open source. So some of them will find mention about MIT at the bottom. So they have a rich repository of articles, slides, videos, etc. regarding artificial intelligence. So I've just picked up some of them from there as well. So as we understand till this point in time, we were all, so what we now want to do is that we want to ensure that computers can start behaving like human beings, and can we actually make the computer learn as we learn as human beings and take decisions that we take as human beings. So how can we actually ensure or make the decision making process as process for a computer totally automated or autonomous? That's what the focus is, right? So now, suppose the most interesting thing here is that if we just talk about image processing, or trying to say for example, sight or vision, all of us have eyes, or human beings, whoever has eyes has the ability to actually look at objects and try to understand whether it is a man, animal, is it a living thing, non-living thing, the locomotion features. So all of this is possible by sight. Once we look at the sight, then it goes into the brain, registered in the brain, and then our synapses, the neurons that are there in our brain has memory, and that fires a trigger over the synapse, and that's how it goes. And we can actually understand, differentiate, and also that can help in making decisions or trying to understand who they are they friends, enemies, etc. All those things happen. So now what we want to do is that if we want to actually make the machine learn, then what are the things that we have to do? So first and foremost, the machine has to first understand the difference between a line and an edge, right? So we as human beings can do that. Then if you're talking about a human face, then if the machine has to understand the human face, the machine has to figure out that what are the features that are there on a face. So the next feature would be eyes, nose, ears, so that it has to figure out. Then once it has the understanding about lines and edges, along with the basic features like ears, eyes, and nose, then it can create a facial structure of a human being, right? And that is what we want the machine to actually do. Now, for to help or to us or to help this or to happen, what so there has been a lot of research which was going on in the field of neural network for decades, right? So as early as 1952, we had the stochastic gradient descent algorithm in place, which was trying to figure out how you could actually optimize a particular situation or a particular given problem. Then we had perceptrons. So perceptrons were artificial neural networks which could actually differentiate between two objects. So if you had some red circles and some blue squares, sorry, I said red circles and blue squares. So can I actually make the machine understand the difference between the two? So perceptrons were actually doing it. Research was going on at a rapid pace, and in 1986 we had the backpropagation algorithms coming into play, where we could actually stack one perceptron over another perceptron, and we could actually have multiple classes being differentiated by machines, right? So in case of the in the initial case, we could differentiate between two classes, right? Whereas in 1986, we could differentiate between multiple classes. So previously, you could maybe, if I talk about the fact that smokers and non-smokers, you could differentiate between that. Now you could even do much more in case of with multi-layer perceptron and backpropagation algorithms. Then in 1995, we had this convoluted neural networks which came into being, and then more and more research has been going on. But as I was talking about, all this has caught the attention of us again because of the fact that big data has become available. So now, if you have to make the machine learn and understand and take decision, first and foremost, you have to feed it with data, as I was talking about. And today, large data sets are available in various forms for various activities, right? Even for healthcare as well, as you all understand and know. Then hardware, as I was talking about, has become cheap, and software is available like TensorFlow, Python, and others, which can actually do the coding and programming for us. Okay, just a minute here. Okay. Okay, so before we proceed, one quick question that I would want to ask is that what is the difference between artificial intelligence, machine learning, and deep uh, deep neural networks, or yeah, deep learning? So, any quick thoughts about this one? AI, machine learning, and deep learning. So, any quick thoughts on these three friends? Artificial intelligence, machine learning, and deep learning. Yes. Can I have some responses from the audience or the participants, please? It will make it more interactive. So, what is the difference between artificial intelligence, machine learning, and deep learning? Any thoughts would be fine. Yeah, can we get some responses, please? Any responses from the participants, please? Okay, so if not, let me explain it like this. So if I draw a Venn diagram here, so this is artificial intelligence. Artificial intelligence means that the machine should start behaving like a human. Now, inside that we have got this one, which is called machine learning. So machine learning is nothing but a set of statistical tools which can be used for finding out patterns in the data. And then inside that you have got a thing called your deep learning, which is nothing but uses ANN, or artificial neural networks, to do the trick for us. Right? That is how it would go. Okay. So is that clear? The difference between artificial intelligence, uh, machine learning, and uh, artificial intelligence, machine learning, and deep learning. Right? So that is how it goes. So the outer part is the artificial intelligence. Then the circle inside is machine learning, and the inner, or the innermost part of it is deep learning. Actually, right? Okay. So let me talk a bit about perceptron, or a bit about neural networks, and then we get into dense neural networks. Right? So, okay. So if I just sorry, let's go. Okay, skip this. Okay, so I think let's deep dive into convolutional neural networks straight away. Okay. So as we were talking about sight, right? Sight is a very important thing for human beings because we can locate objects, we can do motion based on it, and almost all decisions that we take in terms of decisions to differentiate between items or objects are all done by sight or vision, right? So that is how a human being would be doing it, right? So now, if I talk about computers trying to behave like human beings, as we just talked about artificial intelligence, if you still remember the graph, this was artificial intelligence, and here we had machine learning, and inside it we had deep learning, right? So here what we are doing is that suppose we have got some pictures or videos which we are seeing, right? Now this, or which we make available to the machine, right? So that we are making these available to the machine. So the machine sees it, then this is the artificial neural network that gets created or that takes this inputs from the picture or the image that is there in front of them, and based on that it actually tries to train, or it tries to we as individuals and try to train the machine, and the machine should be able to understand various features about the face. So in this case it's finding out the face features of the face, the face, the mouth, the nose, the ear, and the jawline of the individual, right? That's what they're doing. So we can actually be, if we can send a, a sort of data in terms of the various features of the face, then the machine can actually, or the computer can actually learn them through artificial neural network process, and then it can actually then given various other situations, it should be able to understand whether this is the face of a human being or of an animal, or also whether it's a face of a girl or a boy. That's what it can do. Also, if you talk about biology or medicine or healthcare, there are also n number of examples about how a computer can be made to learn from the data and actually interpret. Now, this is, as you, I think you all know better than me, this is a image of a healthy eye, and here we have got an image of a diseased eye, right? So there's a hemorrhage here. So now from this, if I train the system using this data set, and if I give this as a test case, then the system should be able to understand and figure out that there is a disease in this person, and should be actually referring it to some sort of an expert who can take care of this situation. Right? So there's a very useful example at hand. Now you think about driverless cars, as again all of us are aware that Google and others have been trying to work on it, and this has got a phenomenal application uh, of CNN or convoluted neural networks. Because what we are trying to do is that we are providing the car with a lot of prior data in terms of how people who have driven along that road, what were their uh, what were their perceptions about the road. So the perception of the road, the current GPS location, taking them together, we're going to generate a set of convoluted networks. So we'll extract a lot of features out of that image, and then as and when a real situation comes, we will feed it into a deep learning network, and that network will be able to tell the car driver that which path it should take. So whether it should go in this direction, or whether it should go in this direction. Right? So from the data, we're going to extract features. Once we have got the features, we are going to actually then put them into a deep learning neural network, which is going to be a number of stacked artificial neural, or a stack of artificial neural networks, and that should be able to predict and tell us what decisions to be taken at a given point in time. So what computer sees? So computer sees nothing but pixels, right? So it sees pixels, right? So you are saying it in terms of, if it is in grayscale, then it will be like this. So it's a set of zeros and ones, or numbers that a computer sees. So this is a pixel, a representation of an object. So it will be just seeing this number. This is gray, this is black, this is white. So you can put numbers here. So images are numbers and nothing else to a computer. Now, if you have, say, for example, you're talking about, so as you can clearly see here, so there are these are numbers and nothing else, right? So this is 6 is a number here, this is 10, so these are nothing but numbers that would actually be visualized by the machine. Right now, if you're talking about RBG, so if you are talking about a color photograph, then it generally has red, green, and blue tinges on it. So you can have a matrix which is talking about 0 to 255, and each of them would be a number which would be depicting a color scheme in this case. So if you look at this set of pixels that are there, sorry, any questions? Okay. So this is a pixel representation of this image. So if you just look a bit carefully, it is trying to draw a picture of or represent or depict a picture of a human being actually, right? So and if you look at it slightly carefully, it's trying to look like President Lincoln of the United States, right? So it's a image of that. So what they're trying to do here is that they're trying to figure out that can I make the computer understand, or if I train the computer in such a way, then can it differentiate and figure out whether it's Lincoln, Washington, Jefferson, or Obama, right? So what is the so that is what we're going to do here is we're going to train the computer with lots and lots of data in terms of the various in terms of the in terms of pixels, and then based on that can I actually figure out or can I classify this as one of these five people or four people that we're trying to classify them, right? And we'll be assigning some sort of a class score to each of these classes that are there. So Lincoln would be getting the highest one is 0.08. So if you look at it from a bit distance, it looks like with a bearded person, which looks like as close as possible resemblance to Lincoln. That's how you can look at it. Whereas regression, as we all know, is will give us a continuous value. So in this case, it will give us 0 or 1 if it is a two-class problem, or it will give us maybe give us probabilities for 4-class, 5-class, depending on how many classes we are going to separate them or break them into. Whereas in case of regression, what we do is that we would get a continuous value actually, right? So that will actually tell us what is the outcome of it. So we can actually come up with a prediction in terms of y hat, right? So if I say y is equal to say 3x plus 2, and I put the values of x here, then I'll get a estimate value y hat, and depending on what is the difference between y and y hat, so yeah, so y hat and y, or y minus y hat, so we can actually figure out the amount of error which is there, right? So mostly in the case of image processing, what we're trying to do is that we are either going to classify the image into a particular class that we want to, which we are going to do, either which will be leveled and we're going to place it into that class, or so it can be either supervised or unsupervised learning actually. So when you're talking about classification, we are actually talking about supervised learning, right? Now, as we're talking about breaking up things into classes, so what we actually want to do here is that we have to figure out some features and why should that belong to a particular class. So here you've got three images or pictures, right? The first is of a woman, the second is of a vehicle, and the third one is about a house. So how do I actually segregate or separate or classify them into these three objects? So the first one is a human being, and that to a woman. The second one is a jeep, and the third one is a house. So for example, if I have to make the machine understand this is a human being or a woman, then I have to actually talk about their nose, their eyes, their mouth. So these features I should be able to extract from the image. Similarly, if I have to talk about the Jeep, and have made the machine or the neural network understand that the data set should belong to this class, and I have to make it understand based on some parameters or traits of that object. So in this case, wheels, license plate. So mostly cars will have wheels, mostly cars will have a license plate, mostly the cars will have headlights, right? So these features I have to actually make the machine learn. Similarly, when it comes to the house, and if the machine has to understand this is a house, then it has to understand that there are doors, windows, and steps, and these can actually, if these features are there, then we should be able to put it into the group or the class as house. So what we're doing here is that we're trying to extract features or traits or parameters from the image. That's what we're trying to do. So how do we do it? So manual. So if I had to extract features, how do we do it, right? So first and foremost, we have to understand what is the problem that we have had. So if we, so the problem here, first and foremost, we have to have domain knowledge, right? So if I have to figure out that I'm trying to classify houses, right? Or I'm trying to create a database which should be, or an artificial or an AI based app which should be able to differentiate between houses, then I should be an expert in knowing what are the various types of features that a house should have. Right? So domain knowledge is absolutely critical and important. Right? So based on that domain knowledge, I will be able to pick up the features and define the features, and then as and when I need to classify them, I'll be using those features to actually segregate or separate the data points into the classes that I have uh, myself defined using various features. Now we are talking about images. Now it's really difficult to actually make the machine pick up all the various combinations or situations that the picture might have. So for example, there can be various viewpoints in terms of uh, so for example, if you're talking about the statues that you see here, right? So the moment it is picked up from a different angle, then though they're talking about the same image, but if it is viewed from a different angle, the machine should be able to say them apart and understand they are the same thing. So viewpoint variation should not lead to any problem in terms of classification. Now illumination, right? So if the picture is is taken in such a way that the illumination is less, then also we should be able to understand what was being or what are the objects that are there in that, and we should be able to figure that out. So you can clearly see here that the illumination can be different, and it can actually, but we should be able to say very clearly and distinctly that this also belongs to the same class. Similarly, here also we have got two human beings, and both the cases, and they're both carrying a laptop, but the scale is different. One is a very tall person, and the other one is a very short person. But seeing these two images, I should be able, or the machine should be able to understand that it is referring to human beings, and that to men or boys. Similarly, a deformed picture uh, should not be a problem as an input. Should not be a problem as an input, or if it's taken as a part of the training set, it should not give us strong results in terms of classification as we go along. Similarly, if the background is very cluttered, then also we should be able to understand or make the machine understand very clearly that this is a picture of a cat, and the cat is sitting on a mat, which is also equally colorful in nature, and we should be able to differentiate between the cat and the background. Occultation is also another problem that we should be able to take care. And interclass variation is also very important. See, all these are chairs, right? But they have various forms and shapes and sizes. I should be able to understand the intraclass difference. So intraclass variation should be taken care of and understood, and we should be able to understand that these are all chairs actually. So given these things, the machine should be able to classify it as a chair. So picking out the features is so first of all, domain knowledge is very important. Number two, picking up the features are very important, because if I know the features correctly, then only I can actually classify them correctly. But all these things can actually become a bottleneck or point of point which can actually confuse the system or the AI application. So we should be aware of them and take precautions for it when we are building the model. So yeah, so what we have to do here when we're talking about, so if I have to make the machine learn properly or the my AI app learn, so he has to learn, right? So first and foremost, we have to create a hierarchy of features. I'm going to pick up the features in a sequence, and which should actually help me attain my objective. So first and foremost, let us pick up the edges and dark spots, right? So from the image, can I pick up, because these are all pixels actually, can I pick up by some mechanism the edges and dark spots which are there in that image? So that's the first thing that I should be able to do. So this is the low level features that I'm picking up. Then the medium level features is that can I pick up the ears, eyes, nose, etc. from the image. And then finally, can I pick up the facial structure of the individuals whose photographs are being used in the training set. So I should be able to pick up the features from the image at various levels, and then I should be able to create a hierarchical map, and using that hierarchical map, I should be able to say the train the AI system. So how do I learn the visual features? Right. So if I talk about here we're talking about a fully connected a neural network. So by fully connected neural network, this is the input layer. This is the output layer. There are four outputs A, B, C, D. And in this case, there are 1, 2, 3, 4, 5, 6, 7, 8, 8 inputs, right? And there are three hidden layers, H1, H2, and H3, right? So there are three hidden layers that I have here. So there are three hidden layers that I have here, H1, H2, and H3, right? And each of these nodes are connected to the next nodes, right? So when you talk about a fully connected neural network, that means that each neuron is connected to all the other neurons. So this is connected to this is connected to this. So all combinations are possible. So all the all the nodes are connected to each other in this situation. Right? So that's a fully, and not only this, at each layer or at each level, you can find that the neurons are connected to the forward neuron as well. Right? So or the forward layer. So each of the layers are connected to each other using a connection, and that's how a fully connected neural network would look like. So if I just make it very simple, so here let's assume that this is the input layer, or let's call, yeah, this is the input layer. So there are three inputs, x1, x2, or let's assume there are p inputs, x1, x2, and going down to xp. So suppose if it is 3, then this is x3 actually. So now what happens is that this connects to the next neuron. So since it's fully connected, that means this one is connected to this neuron, and this is connected to this again, and this is also connected to this again. Right? So now if I have, so this is a very simple diagram that we have. So we have got weight 1, weight 2, and each of these edges are supposed to have a weight. So weight 1, weight 2, weight 3 in this case, right? Okay. So now, so here what is happening here until this point is that I have got a vector of say x1 to xp, or say if I call x1, x2, and x3, this is information about a particular event which I'm feeding into the artificial neural network, and that artificial neural network should, based on that, learn it and should be able to give me an output in that context. So that is the basic objective of the an artificial neural network. Now, if I have got an image which I want to learn, then how do I do it, right? Because as we just saw, in case of an image, it's a set of pixels that are there, right? So some of it can be one, and they can be numbered within 1 to 255, or it can be shown by +1, -1. So it's just a set of numbers that you actually have. Now, a very interesting thing that we want to do here is that we want to learn, as we said, in a hierarchical manner. So what do we want to learn? We want to learn from the image of the photograph the various features. So first we want to learn the what features we want to learn. So first we want to learn low level features, then we want to learn medium level features, then we want to learn say high level features. Right? So high level features was face, medium level was nose, ear, etc. And this was lines and curves. Right? So that's what we want to learn. So and we want to learn it very correctly so that we can actually we as a machine or an AI tool, we should be able to classify a given image into the required class in which it should correctly belong to. Right? That is what we want to do. So if this is a image, a pixel representation of an image, what we're trying to do here is that we are trying to actually create a patch, right? So this is a patch, and we just want to figure out from this patch what is actually happening in this patch or what feature can be extracted from this patch, right? So there's a big picture that we have here, and from that first picture, we are going to look at it in small patches, and in each of the small patches, we are trying to pick out the features that are there. So we are not picking the full image, and we're not taking the full image and extracting features from it. Rather, what we're doing is that we are looking at a small patch at a given point in time, and then trying to figure out what is the corresponding thing that is happening in that patch and feeding it into a corresponding neuron, right? So that is what we are going to do. So in this case, what will happen is that my artificial neural network or a given neuron or a node in an artificial neural network will only see a particular patch and have information or knowledge or memory about that patch only. That is what we're going to do. Okay, now suppose, so then what will happen is that if this is the big image that I have got with me, so if this is the image that I have got with me, right? So in this case, what is happening is that I will have to create small patches and move that patch window across this entire image to pick up all the information and all the features that are existing in that particular patch, right? So that is what we're going to do here. So if I pick up this patch, which is a 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. So it's a 4 by 4 patch that I have created. So this patch window, I will get a value from this patch window, and I'll put this value into this neuron. Then what I'll do is that I'll skip 2 neurons and put this patch again there. Then again I'll get a value from here, and this value I will put into the second node, right? So this was the first node. This is the second node. I'll put it in. So I'll keep on sliding this patch window over the image, and from that I will pick up some features and store it in a neuron. Right? That is how I'm going to do it. So this is a very interesting way of doing it. So you're not looking at the full picture or the image. Rather, I'm looking at it in small patches, and I'm taking out various uh, features out of it and storing it in various parts of the neurons, right? So say for example, if this is a neural network, so I'm storing one part of information here, the next part of the information here, the next part of the information here, and that's what I'm doing.
Sir, is this process happens in the hidden area or it's in the input layer?
Okay. Okay, so what we're going to do, that's a very interesting point. So what we're going to do here is that we are not going to, yeah, very interesting question. So see, for example, if I look at this one, so this is 4, 5, 6, 7, 8, 9, sorry, if I'm doing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is a 14 by 14 pixel matrix that we have got, right? So what I could have done is that I could have compressed this entire thing and send it as one single vector into the machine, right? I will not do that. Rather, what I will do is that I will actually now put this, I'll create small patches, and then I will set it send this at the input layer. So this will happen at the input layer, and will also happen at the various hidden layers also. So very good question. We'll just look into it in more details as we go on. So the input will be, so we're just extracting features now. Now these features will actually feed into my neural network, right? So that is the difference from when we are just doing it using artificial neural networks. So ANN and CNN has this basic difference, is that in case of CNN, we are extracting the features and then pushing it into the artificial neural network, right? So that's why it will happen at the, we will, first part of this entire exercise is to extract the features. Then the extracted features goes into your input layer of the artificial neural network. Okay. So now let's see how it works. So in this case, so this is called, so this a patch that we're creating is called a filter actually, right? So what does this filter do? So this filter will actually, so this is a 4x4 matrix here. So this filter will actually multiply the weights. So the filter, let's say for example, this is a 4x4, 1, 2, 3, 4x4 filter that we have, say -1, +1, -1, 1, then we have zeros here, and 0, 0, 0, 1, 1, 1, and something of that sort, right? So this is a filter that I have. This filter will we have to will do a one. Sorry, we'll do uh, a point-to-point multiplication with the existing image data, right? That's what we'll do. So suppose if there was a data here, say 5, so this 5 would get multiplied with -1 and become -5. Similarly, if there's a data here 4, this 4 will get multiplied with 0 and become 0, and then we'll add them up all together and put this into this uh, neuron that is there, right? So that is how we are going to do it. So this patchy operation is actually called convolution. So what I'm doing is that I am actually sliding a patch over the image, and I'm then actually doing what a neural network, artificial neural network does, is summation of weight into the the input data that we have, right? So that's what I'm doing here. So that is what these filters actually do. So let us look at this example, the case study about an X. Look at these two images. Both of them are actually talking about an X. So this is a correct looking X, and this is a slightly modified or slightly distorted version of an X, right? But we have to can the computer recognize both of them, though it is shifted, shrunk, rotated, or deformed? Right, and understand that these two are actually X, but nothing else than X, right? That is what we want to actually figure out. So how do we do it? That is the question, right? So as a human being, we can understand that more or less, if you look at it closely, that it is a deformed form of an X on the right side, and you have got a perfect X on the left side, right? So if I just look it from a slightly distance, we might be able to understand the difference between the, or we can say that these two are not different but same. But if it were a computer, it might still have some issues or challenges. So how do I make the computer learn in such a way that it doesn't make a mistake? So the strategy would be as follows, right? So what can I do is that if I can break this up into smaller patches, just like we were just talking about a few minutes ago. So this is one patch, and this is the corresponding patch that you have. So these two look equal. So well, fine. So there's some similarities happening. Then if you pick up this bigger box here, the orange one, you find that this is more or less same, because this is white here, this is black here. So just by basic similarity, this also helps a bit in learning. Then if you look at this part of the stuff, then you can actually figure out that there is some similarity between the two as well here, right? So that is how you can figure out. So now, how do I make the machine learn this? Right? That is a interesting thing here. So let's see how we can do this job. Okay, so suppose I say that the white thing is 1 and the black things are -1. So if I look at along the diagonal, along the diagonal it is all white that's happening. So if I so these are all ones here, and on the off diagonals it's -1 mostly, right? So that is how it's going. So I have to, so what I'm trying to convey here is that we saw it visually. Now, if we had to think in terms of pixels, how would it all look like? So this is all 1, -1, 1. So that's how it is. And this is, so I should be able to uh, make the computer understand in terms of 1 and -1 what is going on. So 1 is nothing but a white space, and -1 is nothing but a black space, right? And if I put the filter on top of it, then I should be able to get this very clearly annotated or understood by the machine. That is the basic objective that I have, right? Okay. So now let us see what is actually happening here, right? So how do I, or how do these filters actually operate? Because the element-wise multiplication that we have to do. So suppose I'm looking at this green chunk here, right? So this is the filter. So the filter is 3 by 3. So this side it is 3, and this side also it is 3. What about this guy? 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's a 9 by 9. So this is a 9 by 9 image. Now, once I put this filter on top of this image, and I'm looking at only this small segment or patch here, right? So let us do the multiplication. It's an element-wise multiplication that you have to do. So 1 times 1 is 1, -1 into -1 is 1, -1 into -1 is 1. This is -1 again into -1 is 1. 1 into 1 is 1. -1 into -1 is 1. -1 again -1 is 1. -1 -1 is 1. And 1 into 1 is 1, right? Okay, clear? Then what we do is that we add this up, right? So here you get 3, here you get 3, here you get 3. So this becomes 9. So what we have essentially done is nothing but element-wise multiplication. So if I say, if I call these elements as W, and if I call this, or say if I call this elements as Xi, each of these, and if I call them as Wi, what I've done Wi into Xi, that's what I've done. Right, and then I've got this 9. So initially I've done Wi into Xi, and then have summed it over these three points, right? So that are three records actually. That's what I've done. Okay, so now these filters are actually a very, very important. So this is a mathematical understanding of the filter, right? Now let's intuitively understand what is going on here, right? So look at this filter here. So this filter has got all ones again here along the diagonals, and across the diagonals, this is 0, and this is 0, and this is 1 that you have here, right? So mostly speaking, or roughly speaking, what is this guy trying to convey is that this is an X. So since it's an X, so you'll have 1, 1, 1 here, and you'll have 1, 1, 1 here, right? So if you look at this one, there's a 1, 1, 1 here. So this is this one. And if you're looking at this one, this is 1, 1, 1 here. So intuitively, I am trying to put a filter on top of the image, and I'm trying to learn the letter X from that image. Right? That's what we're trying to do here. So let's see what's going on here. So if you look at these numbers, 1, 1, 1, these are the actual numbers which are present in the image, or the pixels which are present in the image. And this is nothing but the filter here, right? 1, 0, 1, 0. So this is again along the diagonal and across the diagonal. Right? So this is what is shown here, 1, 1, 1, 1, 1, 1. And that's what it is. So you're just multiplying back and forth. That's what we're going to do, right? So what will happen is that this is 1 into 1 is 1, 1 into 0 is 0, this is 1 into 1, 1. This is 0, this is 1, this is 0, this is 1, this is 0, this is 0. So what are we going to have? So we'll have 1, 1 plus 1, 2 plus 1, 3 plus 1, 4. So this is 4 that we have here, right? So once this patch is on top of this image, I can extract 4. So 4 is nothing but a cross that you're a part of. So it's something like this that you are understood or made the computer understand, right? Now you shift this. So this is nothing. So you move one block here, and again you put the filter on top of it. So this shifting is nothing but a stride, as if I'm walking on this block of pixels, right? So I again come here. So again I do this math here. So 1, 1, 1, 0, 0, 0, 1, 0, 1, 0, 0. So 1 plus 1 plus 1, 3. So I get a 3 here. Now again I move one step this side. So again, I do that math here. So 1, 0, 0, 0, 1, 0, 1, 0, 1. So 1, 2, 3, 4. So again, you get 4, right? So this is how you keep on doing this. And so once you're finished with moving from left to right, then what you do is that you descend one block at a time, right? Then you're moving the filter one block lower and doing the same operation again. So again, that 0 and 1 business. So this is 0, 0, 1, 0, 0, 0, 0, 1. So you've got a 1 here and 1 here. So it becomes 2, right? So that's what is going on. So similarly, again, you do the math, again, you get a 4. When you do this math, you get a 3. So you're just actually picking up picking up features from this entire thing. Right? So net, what have you got? Your filter was like this. You wanted an X to be picked up, right? And you ended up doing that only. So you have got this and this. Roughly, this is what you picked up, right? So broadly speaking, you have been able to capture the letter X from that image or set of pixels that you had, right? So this is called a feature map. So I have just got from that map or that set of pixels an idea about what is being fed or what is being talked about. So I, as a human being, can understand it, but the machine can't understand it. So I'm trying to make the machine understand this on my behalf. Now, now you have this picture of this woman here. Now, if you want to actually get various features out of it, well, anyways, you have to learn it, right? So you have to understand that this is a set of pixels which will be given to the machine, and the machine should be able to understand and differentiate and put it into the right class as human beings, women, etc. So in this case, what you're doing is that you're putting a filter here. Now this filter will actually sharpen the image. Right? If you use this filter, it will detect the edges, as you can clearly see here. So you can get understanding of the edges, the cap, the hair, etc. This will be a very strong edge detector. Right? So if you change the filter, you'll get a different feature from that image. Right? So you are trying to understand, or you're trying to actually create or pull up as many number of features out of that image and store it with you, and then use that to train the machine or the AI application, so that given that similar feature, similar image, it should be able to say or recognize that whether it belongs to one class or onto another class actually. Right? So, and this extraction of feature is very local in nature. Right. So why it is local in nature? Because you are picking it up in patches and then storing it in a given node, right? So as you saw in case of that X also, you picked it up from various parts of that X and stored it in neurons, and or it becomes a memory for that uh, network actually. Right? So you're picking it up and then multiplying it. And on top of it, you're putting the filter, and that filter is magnifying it and storing it as one single number. So for this entire patch, you'll get one single number, as we just saw, right? So you'll get one single number. Then once you move it from, say, if you move it here, you'll get another number for this one, and so on and so forth. You're just creating as many numbers of, or you're extracting as many number of features that is possible from that image. So I think we're doing good in terms of understanding. I hope so. We are getting it right. So, any comments, thoughts, views, friends, as we go along? Okay. So I assume that we are understanding. If not, please feel free to ask questions. Okay, so now we have this input image, and then on top of the input image, we have put a patch, and from that patch, we have extracted a feature, right? So which is called a feature map, right? Now we can have many, if we have got, as we saw, like example, as we kept on moving the patches across it, we got one feature map. Right now, if I change the filter, like we saw a sharp, then we saw, if you just remember this figure, that we got sharp, a feature map for a scenario which was making the photograph sharp. Sometimes we're detecting the edges and strongly detecting the edges as well. Right? So we can get multiple feature maps. Right? So this can be the sharp one, sharp one. This can be the edge one, and the strong edges also. Right? So we can get multiple feature maps based on the filters that we have used. So if you have used multiple filters, we'll get a set of multiple feature maps actually. So that is how it goes. Okay. So again, the same thing here as one of you asking about input node data. So if I talk about this, so this is the input layer. Now I have got, say, for example, a hidden layer here. So, and this is connected to this, and it was connected to this. So there was a hidden layer, and then from the hidden layer, you go to the, say, output layer here, right? Now, there is a, so by convolution, we generate feature maps. So what are we doing? By convolution, we're creating feature maps. So till this point, that's what has happened. So image, on that image, we have put various filters, and with the filter, we have got a lot of feature maps, right? That's what we have got. Now, how do we actually feed it into an artificial neural network, fully connected network? That's what we're going to talk about. So before that, we'll talk a bit about non-linearity, because all these are numbers that we have got. So can we convert it using some sort of a activation function into a non-linear situation so that we can use it? And then how do we do pooling as well? Right? So let's talk about this. Okay, uh, so let's come back here again. So as we understand that, I think all of us have understood the concept of filter, I think, right? So filter is nothing but extracting the feature out of that feature map, right? So that is how it goes, and each one is representing whatever is. So this is neuron one, neuron two, and so on and so forth. That's what is happening here. Now, suppose we have this image here, which has got 32 pixels actually, right? And so that is how it looks like. And now what is happening is that for each and every filter, I will get a one feature map, right? So if there are, it's like 1, 2, 3, 4, 5. So if I've got 5 filters, so filter is equal to 5, then I'll get 5 images or feature maps from that image, right? So of this 32 by 32 matrix or of pixels, I can get 5 feature maps actually coming up, right? So that is how it would be. And uh, so that is the way you can think about. So it's a volume, or it's a set, or a cluster, or it's a volume, or it's a series of filters that which will be applied, and as a result, you will get a series of feature maps actually, right? Now let's talk about the non-linearity part of the story. Because when you talk about neural networks, so neural networks actually have to go through an activation function so that you can give it a connotation of a non-linearity. So it can be a sigmoid function, it can be a logistic function, it can be any function which will actually scale it down into a non-linear value. So now let's look at this. So this is called the most very commonly used activation function in case of CNN is called a ReLU, or is rectified linear unit, right? So it's a very easy function. So what does it do? It says that, well, if you are zero, or if you are less than zero, you become zero, or if you are greater than zero, then you would have the value as it is, right? So that is it. So max of zero or z, right? So if I say max of 0 comma minus 15, then it will become 0. So anything less than 0 becomes 0. Anything above 0 holds the same value as it is. Right? That's how this would actually function. So this actually tries to bring the non-linearity into picture, or non-linearity into the entire process of CNN. Right? So after the convolution operation has been done, or you have generated the set of filters there, now you have the feature maps, and then you can take each of the elements pixel by pixel. You can actually then apply this function, and it will tell you whether it is going to be 0 or it's going to be something uh, which is above 0. Then it will return that value for that pixel. Right? That's how it will go. So this is the input feature map. That's what you have here. So black is negative. So this part is negative, and this part is positive, white part is positive, right? Now, if you take only non-negative values, so this is the rectified image that you have. So you're taking away all the black parts out of the image and only keeping the white parts of the image intact in your features map, right? So this is how the ReLU operation actually works, right? It actually keeps it as it is. So that is how it goes, right? Okay. Okay. So this is how it would be look like. Okay. Okay. Now there's another concept called pooling. So now, as we saw that we can have many feature maps based on the number of kernels or number of filters that we have. And now, if I want to actually still reduce these feature maps that we have, then there's a concept called pooling. So let's see how it works. So this is a feature map that we have got 1, 2, 3, 4, 4 by 4 matrix that you have. Okay, so now what is happening here is that I want to actually reduce and keep the main feature in each of this block, right? So look at this block here. So this is a 2 by 2 max pooling which I'm going to do. So in this block, which is the which is the maximum value, 6 is the maximum value. Put the keep the 6 here. Now take the next block here. In this, which is the maximum, take the 8 here and put it. In this case, which is the maximum, 4 is the maximum, put it here. In this case, which is the maximum, put it here. So this is you are reducing the dimensionality, but you are still storing the essence of that feature map, right? So here, what has happened is that we can clearly see here is that the maximum values have been picked up from that pool, and they have been stored in the post the max pooling activity that has been done. And so they're preserving the spatial invariance, right? So they're preserving the spatial invariance. So let's go back. So that's a very interesting thing. So yes, preserving the spatial invariance, right? So let's think about a image. So like, sorry for my diagram. So suppose this is a cat, right? So you are just storing the cat's face here, and what are the main features that are there that you are storing, and maybe just reducing the feature map a bit, but storing the main feature. So this ear maybe having those high values, then this eyes might be having those high values. So just storing the main features and keeping them intact in the feature map, right? So as we understood, the convolution layer 1 will actually store will actually pick up through various filters, edges and dark spot. That's the first layer of extraction of images. Then this will pass to the next one, and from there you'll get eyes and ears and nose. And then from there you'll get the facial structure of the human being as is in the photograph. Right? So that is how it goes. So let's look at this schematic diagram here. So this part, if you're talking about CNN, has got two parts. One is feature extraction, and the other one is the ANN part, right? So this is the ANN part. So let us talk about this. So this is, suppose it's a car, right? And say an autonomous car which is trying to find its way to various parts of various parts of the streets or the city. So let's see how it goes. So you have got first you have got convolution. So what will happen is that you have the image. From that image, you will create patches, and you will pick up the information. Right now, based on the number of filters that you will have, you will get a series of feature maps, right? So you'll get a series of feature map, right? Now this feature map will then after that you will do the ReLU. That is, you will decide whether to keep the positive values or negative values. You will only be left with positive values because ReLU will throw away all the negative values and make them zeros, right? That will happen. Then after that, what you're going to do, you're going to pooling. As you saw, you reduce the dimension a bit, right? Then this will go to the next layer. There again, from that, whatever you have got, again that will be pulled out, and that will be again going through convolution, ReLU, and pooling. That's how it will go. And this is feature extraction, this is non-linearity, and this is pooling, right? So feature, this is non-linear, and this is pooling, right? So this is how you extract the feature. Then again, that is used by another layer to again extract images, again extract features out of it through convolution. Then you have the pooling, and that's how it keeps on going, right? So pooling is done to preserve the spatial invariance. So you should not lose the essence of the picture when you're reducing the dimensionality. Then finally, what will happen is that so there was a question that whether it's a hidden layer or it is in the input layer. So now the first time around, we are going into the artificial neural network, right? That's the thing that we are now doing. So we are slowly now moving towards the artificial neural network thing. So this is how it operates. So here what will happen is that we will now put it, so now we'll flatten this thing. So whatever we have, we'll just make it into one vector and just push it into the artificial neural network. And then that network will actually behave like any other artificial neural network. And it might use an activation function like softmax, which will actually figure out whether this is belonging to the car, van, bicycle, whichever it is, and will assign probabilities to each of the classes. So that's how it will actually work. This is the code exercise. So I think till this point, I think we have understood briefly what we are trying to do in case of a convoluted network. So we are trying to pull out features from the main image, and then we are passing it into the ReLU. That is your we are trying to then suppress the negative part and keep the positive part of it, and then we are trying to pull it and we are reducing the dimensionality. And then again we are passing it to the next layer. Then again the same thing is getting repeated, and then finally, what we're doing is that we're pushing it into the fully connected artificial neural network, and there we are trying to understand or classify it as the object, whether it is a car, truck, vehicle, etc. That's what we're trying to do. Right? So that is how it operates. Right? Okay, so some applications, yeah, one is detection. So I should be able to detect a particular object using this mechanism, right? As we are talking about whether it's a human being, whether it's an animal, non-living thing, car, truck, bus, whether it's a pavement, so all this we should be able to do. Semantic segmentation also we should be able to do, and end-to-end robotic control that should be also possible in case of if you are applying CNN. So now again going to an example of the medical space. So this is a image of mammography actually to figure out breast cancer. So what it says is that if you pass these pictures these pixels through and CNN, then it is found that the CNN model has done better in most cases compared to the human being, and it's because it has been able to be trained in such a fashion and has seen so many data points and pixels before that it could actually do a better diagnosis than the individual, right? So maybe the algorithm did better at that on that given test set or the given sample space that is there. So it seems to be a lot of prospect and scope, and which can help the medical world in actually reading mammograms and others and speed up things as well. Now, semantic segmentation is again a very interesting thing, right? So here it is not only, so in this case, it was able to say between two things, that is breast cancer and no cancer, right? So it looked at the images and said that so it would classify it into two classes very clearly. But here, it is semantic classification is even very more interesting, much more interesting because it is trying to do something beyond that. So it is trying to figure out the context in which the image is being talked about. Right? So look at this. So there is two cows here, and there is grass, and so this is grass, and there's a two cows you have got, and then here you've got the sky, and you've got some forest here or trees here. Now, can all of this be picked up by the AI, right? So if you do this event, you can clearly see this is grass, this is something else, this is sky, this is cow, right? So this is how you can actually figure out uh, the, the various dimensions that are there in case of a semantic segmentation, and that's possible using a convoluted neural network, right? So it can actually bring out the full context and not only just figure out or identify the object that you're looking ahead to. Again, some cases about brain tumors, right? So the top one is talking about brain tumors. I think you people will be able to understand it and interpret it much better than me. So it's talking about segmentation, and it's talking about exactly where that brain tumor is vis-a-vis the proximity. So the original, the growth truth, and the segmentation that we're talking about. And in the second one, in the blood cells, where are the malaria infections? You can actually find it using semantic segmentation. Right? That is how it is possible. Now you talk about the self-driving cars. This is again a very, very interesting thing because we are now talking about making fully automatic or robotic decision making using yeah, artificial neural networks, no doubt, but convoluted neural networks, right? So what are the inputs that you're taking in this case? The inputs that you're taking in this case are so there's a camera which is mounted on top of the car. So it is spanning the entire region in front of you and getting raw information about all the raw perception about the environment near you, right? So where is the car? What are other cars? Where is the road? Where are the pavements? Where are the houses? Where are the signal points? So all this information is being picked up. And there is also a bird's eye view of that. So one is this one. So this is actual data that you're getting, and this is some coded data, course maps that you have. So in terms of GPS, etc., which you are trying to find out. So GPS locations, etc., will also be picked up. Now then you have all this data together, and then you pool them together, and once you pool, and from each of this you actually pool all this data together, and then can you make the car take decisions on its own, right? That would be a very interesting thing to think about and see, right? So now the car has three things, three decisions: go this way, or this way, right? So it knows it has the actual raw perception, then it has the GPS map, just like we have the Google Maps, etc. And combine them together, can you get it take decisions on its own? So look at this case. So what will happen is that this image that you have, you put it through a convolution thing, and you get some extract some features out of it. This part again, you get some images out of it, right? So you had three roads, right? So three directions you have to have images from that, and three. Yeah, these are the three things. One, two, three. So for three angles, you're taking images, and this is the GPS image that you have. So from this three or four convolution things, you pull out some features, then flatten them and concatenate them together, and then pass it on to your fully connected neural network. So then you pass it to a dense neural network. So this is the feature part, feature extraction part, and this is then the classification or the regression part that you're doing. And once you do that, you should be able to figure out probabilistically or deterministically that what action should you take hereafter. Right? That is how you can think about